Okay, and we're recording. So last time we were talking about just a couple of formalities that kind of have to get said. This first one is easy to misunderstand. We talked about this last time, but I just want to hit the highlights again. Remember the act of differentiation, right? The putting a d before a function, right? What that does is it turns a differentiable function into a matrix, right? And of course, a matrix can be thought of as a function from Rm to Rm in the usual way. Okay, so one thing that you can say is that the derivative, being as the derivative is a matrix, the derivative is linear. And that's, I'm going to say, an easy observation because, well, it's a matrix. That's old news. So what I want to say here is something that sounds, semantically very similar, but is a really importantly different point. And that is, while, of course, obviously the derivative itself is linear, I want to further observe the act of differentiation is also linear. Right? So it's not just when you take linear combinations of input vectors that you multiply by the derivative matrix. Yeah, that's not what we're talking about. When you take linear combinations of functions, right? The act of differentiation is linear. Linear combination of functions in, linear combination of matrices out. In that sense, linear. Okay, so we saw an example of this last time, but I just wanted to sort of segue in to continuing on. So last thing I'm going to say real quick, and this is really just kind of a hand-wave reference. Reminder, tough choices, and I can't spend all the time I'd like talking about every single thing I'd like to talk about. So this is one of the things that doesn't really quite make the cut. This is all very mechanical. Right, so this is a pretty straight read, and furthermore, it's kind of pretty much what you would hope to be true anyway. So, and that is that the act of differentiation, right, also has a product rule and a quotient rule of sorts, depending on the case. So the details, it's all in the book. Make sure to look at that carefully and make sure you understand, in what cases and in what ways can you apply product rules and quotient rules. Okay, all right. So moving along, we're going to talk about higher order partials now. This is, at least the first bit of it is pretty straightforward in the same sense that you can take a derivative of a derivative in single variable calculus. Well, you could do the same with partial derivatives for functions of several variables. It's no deep water, at least at first here. Here's a function. You can take the x partial, the result is a function. You could take the x partial of that, or you could take the y partial of that. Right? No big deal. Okay, so the couple of things that I do need to comment on. First of all, now you'll see I've taken an x partial and a y partial, and then I've taken the x and y partials of each of those. How are we going to distinguish all four of these different second partials? And there's only merely four of them because for this function, there was only two input variables. If there were 7 input variables, there would be 49 different second partials, right? So how are we going to denote this? And unfortunately, even if we write down exactly what seems reasonable, it is actually still a little confusing. So as follows. If I take this x partial, and if I want to represent the act of taking the y partial of that, doesn't this seem like a reasonable notation? It practically reads off the page that we're taking the y partial of the x partial of f. And so with this notation in mind, the shorthand that we use is this right here. You can see how symbolically, just in terms of how it's written on the page, this is just kind of a compact version of this in some sense. So anyway, there it is. Now, here's a different way that I could denote the same thing. This x partial I could denote like that. And then the act of taking the y partial of that, remember we have an alternative notation, which is to, again, have a subscript. And again, with that in mind, the shorthand, that's very common, is to write this subscript notation for a second derivative like this. And again, it's kind of exactly what you would think. There's no big surprises there. Where this gets a little tricky is when you compare these two notations with each other. Notice that the x is on the right of that one, but it's on the left of this one. And the y partial is on the left of that one. It's on the right of that one. And yet these both represent the x partial having been done first, the y partial having been done second. And so that's just pull your hair out, frustrating that it's backwards, right? In some sense, it feels like one of these is right and one of these is wrong, I suppose. I would propose that this is just the consequences of our earlier choices. With this Leibniz notation, we represent the active differentiation on the left. And with this vaguely Newtonian notation here, we represent the active differentiation by a subscript on the right. So there's really no way to avoid this as a result without creating, I would say, more confusion than this. So anyway, keep that in mind. That is a little tricky bit with the notation. Now, the other thing I want to point out, in this case, check it out. These two partials, these two second partials, happen to be exactly the same. How about that for surprising? I think that's pretty surprising. And yet this is not a coincidence. This, I'm going to loosely speaking say, usually works out like this. Now, first let me point out what I mean by this notation down here, describing what I mean by it works out. And then there is an asterisk. There's a condition on this for this to hold that I do need to discuss. But this is just a formal way of representing that if you rearrange if you take all of the same partial differential applications that you're going to do, but you just put them in a different order, then you get the same thing. And this it works asterisk under certain conditions. This works no matter how many partials you're taking. As long as you're just rearranging the partials, but you're still doing all the same partials, then do them in whatever you want. Doesn't matter. Okay, so when do we get this happy conclusion? Well, you get it if the function in question is what we call CK. And you may have actually seen a notation similar to this before. You may have seen in Calc 1 classes they talk about C1 functions and C2 functions. This is just a generalization of that idea. The C stands for continuous, and the superscript tells you how many of the partials also have to not only exist but also be continuous, right? So again, the notation pretty natural in some sense. CK means a function all of whose kth order partials exist, of course, and are also continuous. All right, so if the function is CK, then this will always work. One last little comment about this. You do have to check all of the kth order partials. And a case could be made that, well, if I have to check all of them, isn't that exhausting? I mean, isn't that, oh my gosh, way more trouble than it's worth? Right? Tempting to say that, that's just impractical. But let me point out that very often you can actually check this condition fairly effortlessly, because some categories of functions, their partial derivatives are all in the same category. So, for example, polynomials. I don't actually have to compute bazillions of partials, bazillions of mixed partials, etc., of polynomials to make the simple observation that they are all polynomials. And, of course, polynomials are always defined, and they're always continuous. So this condition, in practice most of the time is actually a lot easier than it looks. Everybody okay with that? Okay, so let's talk about how to visualize, geometrically what do these look like, and we're going to confine our consideration to the picture of graphs, because this is where it makes the most sense, and it's a lot harder to make sense out of in a level set context. So let's start with like fxx. What does fxx look like? Or said differently, if I'm looking at the graph of a function f, what can I conclude about fxx? Simply by looking at this graph. And I will make the observation that if you are interested in fxx, that means that you're treating x as a variable, which means you're treating y as a constant. And good news, you're treating y as a constant for both of the partials that you're going to be computing here. So really, when you take fxx, you are going to just hold y constant. You are then going to look at the cross-section in the x direction. That cross-section will be a curve, which is telling you the single variable function, where f is viewed only as a function of x, because after all, y is constant. And this is just a graph of that function. And so this is a single variable function. Y'all know about second derivatives of single variable functions. This is concave down. That means that this is fxx is negative, just like in Calc 1. Everybody believe it? All right, likewise for fyy, and I'll let you all think that through. Morally equivalent argument. In this case, the punchline is that this is the cross-section you get when you hold x constant and view f as only a function of y. That's concave up, so fyy positive. So okay, those are the highlights, but think through all the rest of the details. Okay. All right. Now, here's where it gets a little tricky. What we see here is extremely familiar, extremely, I'm going to say satisfying in the sense that this is kind of what we were expecting. Second derivatives have to do with concavity. And it's a little weird that there's different concavities in different directions. Okay, sure, things are always a little bit different when you're doing things in higher dimensions. Here's something that's completely different. Thinking about a mixed second partial. What we're about to figure out does not have any sort of, I would call, reasonably understood as an analog in one dimension. There is no single variable version of what I'm about to show you, right? This is new territory. Because in single variable calculus, we don't have two different input variables with respect to which to take derivatives. This isn't such a thing. So what we're going to have to do here, and this is the best way that I know to think this through, we're going to have to take, as it turns out, different interpretations of the two different derivatives we're doing. And again, I'm going to start off looking at partial, let's see, the x partial of the y partial. I'm going to think about the y partial as the slope of the tangent line to the graph in the y direction. So, good news, right? This is kind of what we were hoping. This is our easiest, most familiar way to think about partial derivatives. We're going to think of it as the slope of the graph. Now, notice I can do that because I'm applying that y partial to the function f whose graph I might have access to. Okay. Now, by contrast, how am I going to think about the x partial that I'm going to take of that y partial? And very importantly, disappointingly, I can't think of the x partial as representing a slope of a graph, because I am not going to be looking at the graph of the y partial, right? The thing I'm taking the x partial of is not f. It's the y partial of f. I don't have a graph of the y partial of f. I can't therefore view this x partial as being a slope. So forget about slopes in the x direction. It's not at all what we're going to be talking about for this analysis. Does that make sense to everybody? Okay. So the way we're going to be thinking about the x partial is as a rate of change as I move in the x direction, right? That's one of our alternative interpretations. Thinking about that whole, what I like to call the literal picture of a function, where you have the domain over here, and the target's way over here in a separate world, right? And well, depending, as you move in the domain, there's a resulting movement in the target. We're going to take that point of view on the x partial. Okay, so with all of that set up, here is the resulting picture. Go back to, here we go. Resulting picture here. Actually, I just need this a little bit smaller so it'll all fit on. Okay, thinking about the y partials. Y partials are slope of the graph as I point in the y direction. So here I am looking in the y direction at various different points. You'll see why we're looking at various different points in just a moment. But looking in the y direction, here are the tangent lines that I'm going to presume as I look in the y directions at these various points. Now you're going to notice there is no graph, right, in this picture that I can persuade you these are tangent to. I tried. And it turns out if you try to add the graph in here, the picture just gets more muddled. It just gets more confusing. So use your imagination. There's some surface here, which at these points down here in the domain, these are the tangent lines of the y direction to that surface that, again, I'm not going to draw. Okay, so there's my y partials, and this thing I'm actually interested in is the x partial of that. Now again, x partial, forget about slopes. We're not looking at a graph of the thing we're taking the x partial of. There are no x slopes in this analysis. The way I'm going to understand that x partial is, okay, well, it's how fast is this green thing changing as I move in the x direction. So as I kind of move along, as I'm kind of coming out of the page, if you will, right? These slopes back here, as I come out of the page, those slopes you can see are kind of changing. See my little hand wave here. Okay. Well, I mean, let's just kind of think about some numbers here for a moment. At an eyeball glance, I feel like this back green tangent line has a slope of about, I'm going to say, -2 ballpark. This one here is about -1, roughly. This is about -0.5. This one's about 0. This one's positive, like +0.5 maybe. And so as I move in the x direction, these y slopes are increasing. Said differently, the x partial of the y partial is positive. Everybody on board? It's a little tricky. It's you're combining different geometric perspectives on derivatives all in one little analysis on the same picture. And so it is a lot to be careful about and a lot to, give yourself time to digest. But the punchline is that these tangent lines represent what that looks like. Now, how would I describe this? What I see, again, there's an underlying surface here, the graph of f, that I don't have actually drawn, but I'm going to appeal to your geometric intuition that if I were to have and I've been looking for like a piece of rubber that I can hold up here that actually contort around to kind of look like this. I don't know where to find a piece of stretchy rubber. Anyway, imagine I have a piece of stretchy rubber in my hands, and it's like I'm twisting the rubber, right? And so you can imagine a kind of a twist of sorts in the surface. And so that's what this mixed partial represents. And in general, mixed partials measure a twisting of the graph. And this word torsion is a word that gets used to describe that sometimes, which to me, I feel like there's already a perfectly good word, twisting. So feel free to stick with that. Okay. Everybody okay? All right. Okay. Okay, so we're going to jump ahead real quick now to chapter 3. I do some bouncing around. We've already seen some of the bouncing that I do, right? I did 1.6 early. And anyway, this is another choice. I do this one because the point of view that we're going to get on derivatives of parametric curves in section 3.1, I find really useful in how I like to cover section 2.5. So I'm going to do it first. There's no reason why we can't. And that'll allow me the advantages that I need. So anyway, quick little jump up to chapter 3, and then we'll go back to chapter 5 after this. Okay, so yeah, y'all know what a parametric curve is. Right, it's a function from a single parameter into Rn. Or said differently, it gives position in Rn as a function of a single parameter that I like to think of as time, but you don't have to, but you certainly can. Position is a function of time. Okay, so this is a function. And if you count the input variables and output variables and write down the derivative matrix accordingly, here it is. There's the derivative matrix. It consists of all the, well, just the derivatives of the component functions, the output components. They're all derivatives with respect to, well, the only input variable. And if there's only one input variable, there's nothing to be held constant because there are no other variables. Which means that these are really just plain old Calc 1, just good old-fashioned derivatives. Nothing partial about them. Is that cool? Everybody happy? All right. Now, let's suppose that we never thought of derivative matrices. Let's suppose this was the very first kind of derivative that we ever entertained, was a derivative of a parametric curve. Which, by the way, I mean, you could certainly do this. You could write a multivariable calculus book where this is the very first derivative you talk about. And what's nice about among many things that are nice about doing it this way is, I missed. Let me try that again. Here is what you would naturally, naively write down for how to take the derivative of a parametric curve. The good old regular Calc 1 derivative formula that I'm sure y'all all recognize here. All right, well, this is the derivative matrix. This is the sort of, Calc 1 naive first attempt. And notice they kind of give you the same thing, right? So in other words, if you were to actually do this right here, what you would do is you'd be effectively taking the derivative of your position as a function of time, one coordinate at a time. You would get the same thing as you got from the derivative matrix. So it's a nice little observation that this is a good interpretation of the derivative matrix. In this case, the derivative matrix is literally the Calc 1 derivative of your parametric curve. So that's kind of cool. All right, now, how do we visualize this? And a lot of people think naturally, forgivably, that, if this is a Calc 1 derivative, in Calc 1 we viewed derivatives as slopes, so surely this is a slope of the tangent line or something. But it's not. And again, y'all have heard me say this a million times. I'll probably do it a million more. How you interpret calculus depends on the kind of picture you're drawing. And when, in Calc 1 classes, when they talk about this expression as giving you a slope, it's because they're looking at a graph. And that's not how we understand parametric curves. Parametric curves are not drawn in the, kind of domain and target kind of all smashed together in one axis system like graphs are. We understand parametric curves as living entirely inside of the target. Right, so more bluntly and succinctly, the R here represents t, and yet when you look at a parametric curve, there is no t-axis, is there? Right, if you have x and y as functions of t, that's a parametric curve in the xy plane, no t-axis, It's not a graph. And so, as usual, you can only make interpretations of derivatives if the context matches the intended context, and this doesn't. So this thing here will not be a slope. Excuse me. Okay, so what is it then? The analysis we're going to make actually will be kind of familiar. You will notice that, let's see here, this difference, the difference between 2 points on our parametric curve. Excuse me. And then let's see here, when I divide that by h, that's going to give me a vector pointing in, well, kind of the same direction, maybe a little shorter if h is large. But of course, as h gets smaller, this green vector gets shorter and shorter and shorter and shorter, but I'm dividing by a smaller and smaller and smaller h, and so, this proportion, this fraction here, we expect to kind of level out at some finite magnitude. And then let's see here, as we take a limit, these green differences being what you might call secant vectors, this point here on the right gets closer and closer and closer to this point here on the left, and these secant vectors, the direction becomes more and more a tangent direction to the curve. And so you expect in the limit that all of these blue fraction vectors would just get more and more, and eventually in the limit, tangent to the curve. So there's kind of a picture of what the derivative of a parametric curve looks like. Is everybody on board so far? Everybody's happy? All right. Okay, and now what else can we say about this expression here? And again, this is a tangent vector like that. Tangent is just a fancy way of saying the vector is pointing the direction that the curve is going. Now let's think about the magnitude of this derivative. The magnitude, in the limit anyway, what we're talking about is, let's see here, we're looking at a magnitude of the derivative. So I'm going to take magnitude in the numerator. The numerator represents just distance. It's the distance from one point on the curve to another point on the curve. The denominator here, and I do have a typo here that I didn't have a chance to fix yet. This t here should be an h. That's this h right there. This h right here, which of course is the same as that h, and that h, you'll notice, represents what you might call the elapsed time between where I started and where I went to. So this denominator is effectively elapsed time. And so altogether then, the magnitude of this derivative vector is distance per unit time, which is speed. Again, a familiar idea. So altogether then, we have a vector. We have a vector. This derivative is a vector that points in the direction of the motion and whose magnitude is the speed. That is literally the definition of the velocity vector. And so we have a very satisfying interpretation of a multivariable derivative, and that is that the derivative of a parametric curve gives the velocity of the parametric curve. Does everybody buy it? Okay. Likewise, the derivative of velocity is the physical concept called acceleration, and there's a very analogous argument you can think it through if you'd like. Okay. All right, so this should bring up some kind of familiar old ideas from Calc 1 class. You may recall that there is a category of questions that they give in Calc 1 classes where, all right, we're driving along a road and our, the mile marker that we're at on the road is, how far we are away from our starting point is, given by some following function. Find the car's speed at a given time or whatever. And the big idea is that in that context as described, you're supposed to interpret the function as position and the derivative as velocity, which is awful familiar. It's awful similar to this. In fact, even though they never say this in Calc 1 classes, the reason is that when you describe how far you've driven along the road as a function of time, you are giving position as a function of time. You are actually describing your motion as a parametric curve. It's a parametric curve in one dimension. And so this familiar result is, actually exactly what you should expect. All right for everybody? Notice again, the answer is not slope. Wouldn't make any sense, by the way, to be slope. After all, the derivative is clearly a vector. Slope is not a vector, right? So anyway, clearly not. Okay, let's do one. This is a pretty classical kind of a question. You have velocity given. How do you compute acceleration? No problem. Acceleration is just the derivative of the velocity. You take the derivative one component at a time. Nothing to it. Do make sure that you're good with differentiation. That's in the prerequisite trail of this course. I'm going to assume you're all solid and freshly polished up on how to do derivatives, chain rule and all that kind of stuff. Okay. All right. Okay. Again, given velocity and giving a starting position, what is your position now as a function of time? And this is just an antiderivative. Now you do have to be a little bit careful as you think this through. It's easy to kind of accidentally get it backwards and think through the grammar of how you say it, right? But of course, if velocity is the derivative of position, then position is the antiderivative of velocity, as we have here. Yeah, cool. Is everybody all right with this first step? And again, yada yada. The way you take antiderivatives, just like with derivatives, is one coordinate at a time. So this antiderivative that I want to do to this vector-valued function, just do the antiderivative to the first coordinate and then do it to the second coordinate. No big deal. Don't forget your integration constant. Real easy to forget the plus c at the end. Of course, now we have a vector-valued plus c, or if you prefer, there's a plus c1 in the first coordinate. There's a plus c2 in the second coordinate, all together forming the c vector. Okay. Now, here's where a lot of students mess up. A lot of students, way too many students, seem to think that the integration constant will always be the initial condition. And that's just not true. Now, it might coincidentally work out that way in some cases, and the reason I believe that so many students are under this preposterous misconception is because in high schools, a lot of high schools anyway, they only use polynomials. Polynomials, if you just look down here at what led us to where we were, polynomials, you take any antiderivative of any polynomial, every term will have at least one factor of t. And if there is at least one factor of t, then when you plug in t equals 0, it disappears. And that is a coincidence. It is not a general true statement. Right? And that's what leads to this misimpression. So anyway, please don't accidentally make the mistake of just using the integration, using the initial condition as your integration constant. It's just not true. Okay. All right. So how do we get the integration constant? It's no big deal. We have this general equation here with three terms. X is this function plus an unknown vector c. I'm just going to plug in t equals 0. I'm going to plug in t equals 0 to each of these three terms. Right? Perfectly legal. If this green equation is true for all values of t, then it's certainly true for this value of t. And when you do that, let's see here. This gives me 5, 6 for the left side of the equation. A little bit of arithmetic gives me 3, 1 for those terms. And then, of course, the c is what I'm trying to find in the first place, so that just stays c. And now you have a nice little easy little equation in which you can solve for c, and there it is. C turns out to be 2, 5. Nothing to it. And aside from the fact that this is vectors instead of scalars, this is morally equivalent to the Calc 1 examples that you saw way back when. Everybody all right? Okay. So that's how that goes. Let me point out. Now, again, I've already said this, right? But our integration, integration constant, we call it, right? You see here, very much not equal to the initial condition. Let me clarify that, coincidentally, when this function here is all polynomial, then, this term here will be all zeros, and in that case, the constant will be the initial condition. Now, that's a coincidence, right? So in such a case, your result will be the right result, and you'll still lose points because your reasoning is wrong. Right? You have to actually plug in and evaluate the constant. And if you just say, in such a case where these terms all go away because they're all polynomials, factor of t, even if you have the right result, it is not what this course is about, right? This course is about reasoning. And if your reasoning is not valid and you just get lucky, your reasoning is still not valid, and that's the point. Okay. So I hope that makes sense to everybody. All right. Okay, one last observation I want to make about this, and this is that's just an awkward scenario here, but a lot of people refer to what I have here as being an integral, and it's really not. An integral is a Riemann sum. That's not what we're doing here. What we're doing here is we're undoing a differentiation. Right? V is the derivative of x. I am undoing that differentiation to recover what x was in the first place. This is an antiderivative. Antiderivatives are not the same things as integrals. Now, the reason a lot of students kind of think that they are is because they are very, very, very closely related. And this is a wonderful fact that antiderivatives can be used to compute integrals in many, many, many cases, and that's awesome, right? It's so awesome that they call it the fundamental theorem of calculus. It's kind of a big deal, right? So here's the thing, though. Philosophically, if you're going to get all excited about an important fact that hey, these two things are so closely related, you can't notice that if you view them as being the same thing. There's nothing to be stated. If you view antiderivatives and integrals as being the same thing, what's to state? And then an important truth disappears. It becomes invisible. And that's just really importantly not right. So now I'm aware that there is a term that got popularized, I don't even know when, but to me it's an outrage, that this thing that I have circled right here is sometimes called an indefinite integral, right? That was a reaction to to the observations I've just made about how it's really not an integral, right? Okay, so they call it an indefinite integral instead. And I ask rhetorically, what's to be gained from calling this an indefinite integral? when in fact it's just an antiderivative. There's no need to try to cling to this conflation of two importantly different things. So anyway, I think this is a big deal. I hope you will exert the same efforts that I do in trying to distinguish an antiderivative from an integral. And we have not even begun to talk about integrals yet. Multivariable integrals are a very different thing. And by the way, one thing you're going to notice when we get to multivariable integrals, they are really not the same thing as antiderivatives, really in any sense. They're totally different, right? So this is a good groundwork to lay before we get to that point. So I got brought up the wrong way as well, by the way. I grew up, mathematically that is, calling this an integral. I've been fighting it in my own mind ever since, and I encourage you to as well. Okay. Alrighty, so we move on now to, one last comment. So y'all will recall the content syllabus for the course describes what you are and are not responsible for, what is and is not part of the course. And as is noted on the content syllabus, we're going to be pretty much skipping, I'm going to say, a sizable chunk of section 3.1. It is classical and historically important mathematics. It's very cool, right? And I'm glad that Colley put it in the book. But we don't have the time. It's not where we're going with the material. You don't really need it in that sense, and we just don't have time. That would be a luxury that we can't afford, right? So by and large, you're going to be skipping the Kepler stuff. But that said, there is one important result in that section that you do need, and so you are responsible for this theorem. And good news, it's exactly what you would expect. And if you're taking a derivative of a dot product or a derivative of a cross product of two vector-valued functions, there's in each case a product rule that's exactly what you would hope and expect that it would be. So do make sure to look at that one result, think it through, persuade yourself that of course this is going to work out, and everything else in the Kepler section you can ignore. Okay, so moving along. Back to Chapter 2, Section 2.5, the chain rule. So, I know y'all know the single variable chain rule. I'm nevertheless going to spend a page of notes talking about the single variable chain rule, not because I think you don't know it. I know you do. The reason I'm going to do this, and by the way, this is the first example of several, I think very often it is valuable to take a particular, specific, narrow perspective on something that you already know. Because from that perspective, extending to the multivariable context is easy and natural and it's the exact same thing. And it makes understanding the multivariable concept, I think, quite a bit easier. So again, I'm going to give you, the point here is not to teach you the single variable chain rule. I know you know that. That's fine. That's cool. The purpose here is to focus your point of view on the single variable chain rule to a certain very specific perspective. So here we go. Here is that perspective. Recall that a derivative, among many other interpretations you can take of a derivative, is it relates velocities. So an input velocity and an output velocity. And you might say here in this, the way I have things set up here, with f being a function that takes x as an input to y as an output, and if both of those are functions of time, then dy dx is what you multiply by input velocity to get output velocity. Is that cool? So please, for the purposes of this page that we're about to do, please don't think of derivatives as slopes, right? Please think of also don't think of derivatives as fractions. we want to think of a derivative as being a factor. And again, I know it's kind of the same, but very importantly, we're going to think of it here as being a factor that you multiply by input change to get output change. All right, and with that perspective noted, let's look at this scenario here. We're going to look at what I'm going to call a sequence of two functions. Here I have f that takes x as an input, gives me y as an output. And then immediately following that, I'm going to take that y that was an output from f. I'm going to let that be the input to g, with output being z. So this is kind of a Lego sort of fitting together of two functions. What comes out of the f goes in to the g. Now when you do this, you can talk about the composition. And the composition is a function that will all at once, in some sense, take x as the input and then do both of the functions to result then with z as the output. Is that cool? So we actually have three functions on the board here. We have f, we have g, we have the composition. Okay. All right. Okay, so now each one of these three equations that I have written down here is no big deal. Each one of these three equations is just what we were talking about before. A derivative is a factor that you multiply by input change to get output change. That's it. Nothing else happening here. Right? Just as a for example, let's look at number 2 here. Number 2 is about the function g, which takes y prime as my input velocity and z prime as my output velocity, and the derivative of g, dz dy, is what I multiply by y prime to get z prime. So again, it's just exactly the point of view we had above. Is everybody happy with that? Okay. All right. And I know there's a lot of arrows and a lot of, there's a lot on the page, but ultimately this is just three examples of the above formula. So the what I'm going to do to make the algebra work out on this is I'm going to take this formula for y prime and put it in to where that y prime is. I'm going to say plugging equation 1 into equation 2. That results in this right here. And then I'm going to compare this equation with this equation. And look at these two equations I have highlighted in blue. This equation down here tells me what to multiply by x prime to get z prime. And this equation over here also tells me what to multiply by x prime to get z prime. Okay? And that being noticed, that means that these two things being what I multiply by x prime to get z prime, those two things must be equal, and thus we get our chain rule, the Leibniz form of the chain rule that I'm sure you all recognize. Is that cool? Right? Everybody happy? Okay. I like to call this no surprise, because altogether, however you choose to think about this, when you start with x prime and want to get to z prime, you can think of that two different ways. I multiply by f prime and then I multiply by g prime, all of which is equivalent to multiplying by the derivative of the composition. So, therefore, same thing. Everybody happy with that? Okay. All right, so this is, again, a very particular point of view on single variable chain rule, and what we're going to find on Wednesday is that there is a very, very analogous point of view on multivariable compositions and differentiating multivariable compositions, and we will get a multivariable chain rule. So, okay, picking up there next time. See y'all later. Have a good one. Reminder, of course, if you came in after I did attendance, make sure I check you off. Okay.